So, we're all on this global mission, right? To build a 100% clean energy grid powered by things like solar and wind. But, and this is a big but, there's this hidden challenge lurking in the background. It's a really deep engineering problem that, if we don't get it right, could actually threaten the reliability of our power.
Yeah, it sounds totally backwards, doesn't it? The more clean energy we add, the more fragile the system could become. So in this explainer, we're going to break down exactly why that is, and more importantly, how we can build a clean energy grid that's not just powerful, but also super stable and secure.
All right, let's dive into this. To really get a handle on the challenge we're facing now, we've actually got to go back in time a bit. We need to understand the secret sauce that made the old grid so unbelievably tough for over 100 years.
And that secret sauce, that anchor, has a name: inertia. I want you to picture these absolutely massive, heavy turbines spinning inside an old-school coal or gas power plant. The sheer physical momentum of all that spinning metal acted like a giant natural shock absorber for the entire grid. It just automatically smoothed out any sudden bumps. And this is where you can really see the huge shift. Old power plants, heavy spinning metal, high inertia. It was just part of the package, totally free. But solar and wind farms, they're completely different. They connect to the grid using electronic inverters. And because these are just solid-state electronics, silicon and copper, no big moving parts, they have, you guessed it, zero inherent physical inertia. None. Okay, so that is the heart of the problem. Every time we switch off an old high-inertia power plant and switch on a new zero-inertia solar farm, we're literally pulling one of those natural shock absorbers out of the system. So, what happens when you do that on a massive scale?
Well, to get it, you have to think of the grid as having a heartbeat. That heartbeat is its frequency. In Europe, for example, it's supposed to beat at a super steady 50 hertz. But if a big power plant suddenly trips offline, you get this power deficit, an imbalance, and that heartbeat, it immediately starts to slow down.
And this is where it gets pretty scary. It's all about how fast that heartbeat slows down. In a grid with high inertia, that drop is slow, kind of graceful even. It gives grid operators precious seconds to see the problem, bring backup power online, and stabilize everything. But in a low inertia grid, that drop is crazy fast. The reaction time shrinks from seconds to milliseconds. There's almost no time to react.
And there is a red line you just cannot cross. In the big continental European system, that number is 49 hertz. If the frequency dips that low, alarms are screaming. Automatic safety systems kick in and start doing the one thing they're designed to avoid: load shedding. And yeah, that's just a technical way of saying they start intentionally cutting your power off to save the rest of the grid.
So let's take this to its logical conclusion. What's the absolute worst-case scenario here? If these automatic defenses aren't fast enough, what happens next?
It's as simple as that. Without that inertia, the whole system becomes brittle. A single fault can spiral out of control, creating a domino effect that could take down the entire interconnected power system, not just a city, the whole thing.
Okay, so that's the risk, a fragile grid prone to collapse. But here's the good news. This is absolutely not an unsolvable problem. In fact, for engineers, this is a fascinating design challenge. We just have to stop taking stability for granted and start intentionally building those defenses that the old grid used to give us for free. We do this with something called system services. The easiest way to think about it is like a toolkit, a menu of specific technical capabilities that we can use to keep the grid's heartbeat steady. We're essentially rebuilding the grid's immune system from scratch. And the tools we have now are pretty amazing. We've got grid-forming inverters, which are basically super smart electronics that can program a solar farm to act like a traditional generator, creating what we call synthetic inertia. We've got huge battery storage systems that can inject massive amounts of power in milliseconds to stop a frequency drop cold. And then there's this really cool tech called synchronous condensers. They're like the big spinning part of a generator, but with no engine. They just spin, pumping pure, stabilizing physical inertia back into the grid without burning any fuel. How cool is that?
So, we've got the tech. We know how to solve this. But the big question now isn't really a technical one anymore, it's a strategic one. How do we make sure these solutions get deployed at the right time, in the right place, and at the huge scale that we need?
And this brings us to the central policy debate. Do we just make stability a mandatory requirement for every new solar and wind project that gets built? Or do we create these specialized markets where the grid operator can actually buy stability services from whoever can provide them the cheapest?
We're looking at two really different paths here. The mandatory rules approach is pretty straightforward. Everybody has to do it. But that could drive up the cost of every new renewable project. The alternative, creating a market, is exciting because competition could find the lowest cost solutions. But designing and regulating these complex new markets, well, that's a major challenge for policymakers.
So where does that leave us? Given these choices, what are the experts who study these complex systems saying is the best way to go?
Well, the consensus seems to be landing on a smart hybrid approach. First, for the really specialized and expensive services like inertia, the recommendation is to use markets, like auctions, to let different solutions compete and drive down costs. Second, for some of the foundational capabilities, like basic voltage support, it just makes sense to make those a mandatory, non-negotiable standard for everyone. And finally, and this is critical, we need to do a lot more detailed studies to figure out exactly how much of each service we need and where.
So, at the end of the day, here's the real takeaway. Building a 100% clean and reliable grid isn't just about installing more solar panels and wind turbines. It's a challenge of intelligent design. Success really depends on how we build it, marrying our new energy sources with smart policies and engineering that recreate that invisible stability we used to take for granted.
You know, this whole inertia problem was hiding in plain sight for decades, and now we have to consciously re-engineer it. It leaves us with a pretty important final question to think about. As we keep transforming our world to run on clean energy, what other invisible systems, what other hidden anchors are we going to discover that we need to reinvent along the way?